Hello, Physics Nation. My name is Nate Larmond, and I'd like to do a second sample calculation for the Do-It-Yourself Projectile Launcher Lab. We just did the horizontally launched projectile. Here's Newton's Daydream that sort of previewed satellite motion. Here's the Harvard demonstration with the shot pool ball and the horizontally launched pool ball. This guy's more or less horizontally launched, the straw flicking the cotton balls, but Harvard's second demonstration, the so-called shoot the monkey, where is it? Yeah, shoot the monkey. This hyperlink um, is diagonally launched. So that's our second calculation. For the first experiment, we were shooting horizontally. Now we're going to shoot diagonally. So what are we going to mess with? Well, we're going to mess with the launch angle. So we're going to change the steepness. We're going to go from very shallow launch angles to very steep launch angles. Again, you could do it in the PhET simulation if you wanted. Where's that? This guy. If you want to do the PhET simulation, there's nothing wrong with that. But shooting real projectiles produces much more interesting data, much more complicated data, much more messy, uncertain data. You know, this is an algorithm. Somebody programmed mathematical models into this, and so it follows those mathematical models very cleanly, but real systems are a little bit more complicated than those mathematical models. So I really suggest you build something cool and launch some projectiles. Anyway, like I said, this is the sample calculation, so we always do a sketch. We always explicitly state the question. We're going to measure three things: altitude, range, and flight time, and see how they are affected by changes in launch angle. Okay, so we're going to shoot this thing steeper, 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 and see the effect on altitude. How many meters high does it go? Range, that is its change in horizontal position, and how long it's in the air. So really no calculated values. The only sort of calculation is the launch angle. You may or may not have a protractor, but you don't really need a protractor. You can stick to these 5 magic angles. How do you measure angle with only a ruler? Well, it's simple. The ratio of the sides of a right triangle describe the angle. So I should put this up here with the initial resources. All the way down here is a PhET simulation called Trig Tour, and it's pretty awesome. So you can put a right triangle within this circle, and the radius is 1. So check it out. If you want 30 degrees, let's dial in 30 degrees, all you have to do is make this ratio, y, the height of this right triangle, to be 50% of the length of the hypotenuse. That's what sine of theta means. It's just the ratio of two sides of a right triangle. This guy, the opposite leg, this is the angle we're describing. So the green guy is the opposite, and the hypotenuse is 1. They call this the unit circle. So my hypotenuse is my clipboard. It does not have a radius of 1. It has a radius of, let me see if I can get this on camera. It has a radius of about 13 inches. Whoops. There we go. So roughly 13 inches. All right. So how do we dial in 30 degrees? Well, if the ratio of the height, that is this dimension, to the hypotenuse is 0.5, all you have to do is you multiply the hypotenuse by 0.5, and that'll tell you the height. So half of 13 is 6.5. Is that 6.5? Right there. That's a launch angle of 30 degrees. No protractor. How about 45 degrees? Well, that ratio is different. It's actually root 2 over 2, approximated to 0.71. So 71% of the hypotenuse is the height of this triangle, which is 9.2 right there. That's 45 degrees. How about 60 degrees? Well, that ratio is root 3 over 2, or 0.866, or 0.87. What's 87% of 13? 11.25. So right there, that's a launch angle of 60 degrees. And honestly, those ratios are the only calculation for this experiment. So there's the sample calculation.